Well, the impact of Natta's research work, along with that of Ziegler, of course, was transformative. It was a game-changing event, and they were honored with the Nobel Prize in 1963, and I was in my third year as an undergraduate student at Edinburgh. And it was then that I learned about polypropylene and the importance of the orientation of the methyl groups on the polypropylene, so that I learned about three types of polypropylene. There was isotactic, when all the methyl groups were lined up on the same side. There was synditactic, when they were alternating on each side of the polymer chain. And then there was the one that was a mixture, which was called atactic. It was, and I think remains to be amorphous material, whereas the other two are crystalline. And I was a student of stereochemistry, and so I was just absolutely thrilled with the fact that somebody had been able, i.e. Natta, to unravel the stereochemistry. Molecular machines are in their infancy. If you want me to talk about potential applications, I will say, well, first of all, they will have an enormous effect on chemistry, and I come back to stereochemistry, particularly those that are based on the mechanical bond. The mechanical bond gives to molecules a new source of creating chemistry in space, i.e. stereochemistry, that is dependent on not stereogenic centers, but on what Prelog christened as axes and planes of chirality, as well as helicochirality. So we are witnessing another revolution in stereochemistry. The again, mechanical bond in the form of polymers, which I will talk about today, called rotaxanes, is revolutionizing material science. And so they're already on the market in Japan, polymers that are scratch resistant because of the way the rings move along polymer chains when you create a scratch. And after, of course, the scratch has been implanted, the polymer then adjusts and sends the rings back to fill up the scratch. I think the ultimate application, though, will be in medical science, where we will see the birth of what I call molecular prosthetics, where these little molecular machines will actually address our bodies at the cellular level. And we will have what I sometimes refer to the birth of molecular prosthetics. We're all familiar with heart transplants and kidney transplants and liver transplants, and also knee joints and hip joints being replaced. But now we are going to be able to do very, very similar types of surgery and the delivery of drugs to the cells themselves. So we're going down to the very, very ultimate level of, if you like, life. The art of supramolecular chemistry is all about working very close to equilibrium, and what you do can be undone very quickly. So it is there that we are going to, I think, find refuge for coming back to polymers that are not going to live on in our environment the way the first polymers do, polythene and polypropylene, and this brings us back to Natta, of course. We're going to see biodegradable polymers, for example, as a result of the advent of what I would call supramolecular polymerization. So it's not only changing the materials that we have in our lives, but supramolecular chemistry is changing the way we think about chemistry. And from my point of view, it opened up the possibility of making a new bond, the mechanical bond. And it's on the back of supramolecular chemistry that the mechanical bond has been established, and the molecular machinery that myself and Jean-Pierre Sauvage have brought to chemistry were built.